Well, good morning, good evening, good afternoon from wherever you are. My name is Kendall Youngworth for those of you who are just joining. I am one of the Sherwin-Williams Marcom managers for our water infrastructure segment, and I will be the moderator for today's webinar. So welcome and thank you for attending. I did want to welcome you to our September webinar, and this is our second to last webinar of 2024. Our last one will be next month in October. But today we'll be discussing what is algae, how can it affect water infrastructure, and how to effectively control it. And we're really lucky to have our two marketing segment managers, Heather Steiner and Steve Roeder, presenting today's webinar. Before we get started, I would like to just mention a few housekeeping items. So you may have noticed that we've moved from GoToWebinar to Teams. For those of you who had to re-register, we are sorry for any inconvenience that this may have caused. And also, typically, for those of you who have attended these in the past, we do multiple poll questions throughout the webinar, but today we will forgo the poll questions. We do hope to have this reinstated into our 2025 webinar series, though. If you do have a question during the presentation, please submit it in the Q&A section. And at the end of the presentation, we will answer as many as we can. And then in terms of the recording and the presentation deck, you will not be able to access them through Teams like you could through GoToWebinar, but you will receive an email within the next couple days, which will have a link to the recording and to a PDF version of the presentation. And then you will also receive a separate email, which will contain your PDH credit. So with that being said, I will turn it over to none other than Heather and Steve to talk about algae. Thanks, guys.
Thank you, Kendall. So real quick, just a quick introduction of myself. I am Heather Steiner. I'm the market segment manager for the Water Infrastructure Group here at Sherwin-Williams. I have been with Sherwin for about 6 years now, and the entire time I have been dedicated to the Water Infrastructure Group. And I want to thank everybody for taking the time today to listen to Steve and I. And with that, I'm going to pass it over to Steve to introduce himself.
Thanks, Heather. Yeah, I'm Steve Roeder, other market segment manager for water infrastructure, which covers water and wastewater. I've been with Sherwin-Williams now for about 5.5 years, but I have a total of 40 years in the water wastewater industry. So I've been knocking around for quite a while. What we're going to talk about today, the objectives or the outline, is algae, right? And how it affects specifically wastewater treatment facilities, and one of the ways we've come up with to control the buildup of algae in these systems. So we'll talk a little bit about what it is and what it does. We saw early on the coating we're going to be talking about is Sherloxane 800 polysiloxane, that it had the ability or it didn't allow biological growth to grab a hold of it. So what we did was we did a little study internally to figure out why that was the case. So a lot of what we're going to talk about later in the presentation, under what we found and methods of control are the results of that study that validated what we were seeing out in the marketplace with the polysiloxane. So I'll let Heather start off here, and here we go.
Yeah. So whenever you're at a treatment facility and you're walking around the plant, oftentimes you're probably noticing a blue greenish type film gathering on top of the water. And a lot of times you might be trying to figure out what exactly that is. So I want to just take a moment here to define what algae actually is. Algae is considered a aquatic organism in itself. And just like most aquatic organisms, in order for it to grow and survive, it needs sunlight, water, and carbon dioxide. And then what it ends up doing in that growth process is it's going to create oxygen and energy. And actually, a lot of the oxygen that we get supplied out in, you know, the normal earth is actually created through the algae process. But the big thing about this is the photosynthesis process. It requires sunlight. So a lot of times when you're seeing this algae buildup, it's going to be in areas of structures where it is outdoors. So you're talking like your clarifier launders, or you might see it build up on some of the weirs when you're walking around your facility. One thing I do want to point out, it's in red highlighted here on this slide, is I know that there are methods out there with ways to try to treat the algae aside from using coatings, and one is increasing the oxygen in the water. I just want to point out that that is going to help reduce or slow down the growth of the algae itself, but it's not going to eliminate it totally altogether. Next slide. Okay, so I already brought up how it needs light to grow and build up its energy, but there's other key things that helps the algae to grow or cause it to, you know, stunt its growth. So nitrogen and phosphorus are nutrients that are helpful in the growth of algae, and they play a pretty crucial role in how much it grows and how much is produced. So being able to control that amount of nitrogen and phosphorus that goes into the treatment process or the water process is helpful. Low oxygen in the water can also help with creating the algae to grow as well. And then light and temperatures are equally significant factors in the growth process. Algae will thrive in environments, obviously, with optimal light intensity, and also the intent, you know, the longer that it's daylight, the better. Can you go back? Thanks. Higher water temperatures. So if you're in a situation where you're in a geographical region where it tends to be warmer or the temperatures tend to be higher, that you have a higher probability of your algae to grow as well. And then you also, chemical treating the algae can lead to reproduction. A lot of times, if you look at your pH levels, you can make a determination on if the algae is going to continue to grow or if you're going to be able to stunt that growth. pH levels and carbon dioxide concentrations will impact that algae growth. The more alkaline to neutral pH, the better for the algae growth, and it helps with the metabolic process affecting the growth as well. Next slide. So like I said on the previous slide at the beginning, there are harmful effects with algae. When algae builds up, it can cause blockage or reduction in the flow in the weirs, pipes, influence, effluents. I do want to point out that for the purpose of this presentation, we are talking about blue-green algae, and that algae is going to it can build up in water treatment or wastewater treatment. But the solutions that we're going to be talking today are going to be dealing with polysiloxane coatings, which are not NSF approved. So we're going to be focusing mainly on wastewater treatment plants. And then, Steve,
sorry,
can you go
Heather,
back?
it's getting away from me here.
That's okay.
Yeah. Were we here?
Yeah. So whenever you get that buildup of growth, one of the problems, it's kind of a domino effect because you get the buildup of growth, which is going to cause a reduction in the efficiency of how those parts of the plant are working. And then it also creates more sludge and disposal. And then in the end, that's going to create an overall additional cost for operation of the plant. So there's a lot of benefits to being able to slow down the algae growth or to you know, come up with unique ways to be able to control it. Go ahead, next slide. Harmful effects. So this goes along with, on this slide, I'm going to talk about how it can affect the consumer in regards to poor water clarity. It can cause an odor that at times can almost make someone get nauseated. And it can impact the water taste and the quality in the water treatment process. But like I said, this slide is, we want to point out that these are factors with algae growth in the water treatment slide. But however, today's presentation is going to be focusing on the wastewater side, mainly because the coating we'll be talking about is not NSF approved. So with that, I'm going to pass it back over to Steve, and he's going to talk a little bit about a study that we did.
Yeah, so we had seen for a number of years that the polysiloxanes had a lot of characteristics of foul release coatings that are used in like the marine industry. And there was a lot of anecdotal evidence that using this coating, especially in clarifier launders, it doesn't stop the algae from growing, but what it did was it made it easier to clean it off. Whereas what owners were finding is if they had to go in with a pressure washer and spend a day and a half with a high pressure cleaning the walls of the launders, with the polysiloxane coating, they could go in with just a regular garden hose pressure and clean it off in a matter of an hour or two. So it significantly reduced the amount of effort required to clean the algae off of the walls. So we saw this anecdotal evidence. So we decided to do a little internal study to try to figure out why it worked, to validate it, so that if we made any claims, we could back them up. So we got an owner to participate, and we went into the clarifier and we sampled the algae that was growing in the clarifier, first of all, to find out what kind of algae was in there, right? And we found exactly what we expected to find, which was basically three different types. It was dominated by what they call filamentous green algae of the genus Microspora. I know that doesn't mean anything to anybody. Means very little to me as well. And then there were two. That is the kind of algae that forms into long strands, right? There were two major other ones present, which are diatoms, which are algae that just form into cells and float around in the water. But interesting enough, what they do is they attach on to the filamentous algae, and they bulk it up, compete for the sunlight and the nutrients, and make the bulk of the algae what it is and what causes the problems. A lot of times, these groups of algae will break off. They'll clog up pumps. They have destroyed pumps at times, clogs the system up, and reduces the efficiency of the treatment system. So we found exactly what we expected to see. We also found the cyanobacteria that was mentioned, which are not really algae, but they look like algae, but they actually create put off byproducts, sometimes poisonous, sometimes cause taste and odor problems in potable water systems. This, unfortunately, our solution won't work for potable water. So currently, what you'll find is, if you're an owner, you already know this as well. There are several systems, methods that they currently use to try to control the growth of the algae. One is a brush system, where they attach brushes to the end of to the mechanisms that push up against the wall of the launder or the wall of the clarifier, and as the mechanisms spin around the clarifier, it cleans off the surface as it goes. These are effective, but they're an additional cost and additional maintenance issue, and they can actually lead to erosion of the coating and the structure over time, because that slow movement over time will cause erosion of the coating, erosion and then of the concrete below it if there's no coating. There's a number of chemicals that they can dump in that will that can kill the algae. They have found sometimes that actually promotes the growth of the cyanobacteria because it limits the competition for the sunlight and the nutrients. So you take care of one problem and another one comes behind it to flourish. It can also throw off the system by adding chemicals to the treatment process that aren't accounted for in the treatment system. Some of them would have to be removed after before just discharging the water. Manual cleaning and removal, that's this process that we help with the coating. Aeration, baffles, filtering, that helps, but it does not, it can help to control the growth, but it won't prevent the growth of the algae. And then the covers. Covers are really expensive. You see them a lot. The thought is that by preventing the sunlight from getting to the surface, you deprive the algae of one of its sources of nutrients, the photosynthesis. It doesn't require direct sunlight, so again, you can still get some algae growth underneath the covers. Covers are expensive, and one of the big problems is if this is an area where you have hydrogen sulfide still dissolved in the waste flow, this H2S can be contained by the covers, concentrating it and leading to worse biogenic sulfide corrosion of the concrete. So all of them effective to a certain level. All of them have their own drawbacks, right? The advantages that we have found working with owners for an algae release coating or a bio release coating is that the targeted solution can be used in most of the processes in wastewater where algae growth is an issue. It doesn't require any additional treatment or chemicals. Reduces the manpower required to deal with this algae problem. And I've got a short little video to show you how that works. It's an easy solution, minimal upfront cost. And one of the additional things is that this coat of paint actually adds additional corrosion protection to the surfaces that it's applied to. The polysiloxane is a hybrid, sort of a hybrid between a polyurethane and an epoxy. So it has it has barrier protection and it has color and gloss retention. And color and gloss really isn't a critical issue inside of a wastewater treatment plant, but most of the coatings that we use for barrier protection, epoxies, are not UV stable. In other words, the UV light will over time break them down in chalk and they'll eventually disappear. You lose about 1 mil a year of epoxy in direct sunlight. So what this polysiloxane does is it protects that underlying epoxy from the effects of the sun, and it will actually significantly extend the life cycle of the coating. Yep, and I just said most of that before I got to the slide. So it again enhances protection of the asset. One thing I didn't mention, it can improve the flow characteristics because of its smoothness and its low surface energy. It can enhance the flow characteristics of whatever facility is put into. And this is some of the anecdotal evidence that we saw early on. It works really well on the outsides of water tanks to reduce the buildup of the biologic growth from the condensation of the sweating on the exterior of the tank, and dirt buildup as well. It becomes self-cleaning from the rain. If you look at the right-hand photograph, you'll see a cascade aerator at a wastewater treatment plant. The far wall, the lighter, brighter blue is the polysiloxane. The blue that's on the nearer wall is a polyurethane coating commonly used. They were both in service for the same period of time. They were both of those walls were done at the same time. And you can see that the polysiloxane wall remains clean just from the scouring action of the water going down the cascade aerator. And you can see the buildup of the biological growth on that near wall. So I'm not suggesting necessarily that the biological growth on that near wall is a problem. It was just some of the anecdotal evidence that we were seeing that seemed to indicate that the polysiloxanes did a much better job at releasing the biological growth than other coatings did. And this is one of the pilot projects we did to kind of demonstrate the how easy the algae is to clean from the polysiloxane. Let me see. Shout out to Annie Hoagland for uploading that to YouTube for us. But this is pretty typical of what you get. It doesn't prevent the growth of algae. What the polysiloxane does is makes cleaning it much, much, much easier. those of you that have ever had to clean algae from a launder and a clarifier will understand just how big of an improvement that video was. So turn it back over to Heather here to talk a little bit about how.
Okay. So I am going to talk now a little bit about how Sherwin-Williams decided to attack and try to solve this problem. So we decided that we wanted to solve the issue with algae and try to create a algae release coating. And so for doing that, we started a project where we evaluated several different coatings and looked at two key things: surface energy and surface roughness. So the next several slides, we'll be talking about the details of that study. But real quick, when we refer to surface energy, that is basically the propensity of something to be able to reject water. So if you think of a freshly waxed car, and whenever you would put water on top of that freshly waxed car, the water tends to bead up and flow off. This is an indication that you have low surface energy. So whenever we're looking at these coatings, we know that we need the coatings to have a low surface energy. And then we also want to look at surface roughness. Think of surface roughness the same as you would with a profile. You're talking about the peaks and valleys that might be within the substrate. For the purpose of algae release coatings, you want it to be as smooth as possible. So we will be, those are the two key things that we looked at in this study of ours. Next slide. So the main coating systems that we looked at in the study were siloxane 800, which is our polysiloxane. And then we did look at a competitor's version of polysiloxane. And for the purpose of this presentation, we'll refer to that as polysiloxane B. And then we pulled the workhorse coating that we use a lot in the wastewater side of the business and looked at an amine epoxy. And then we also looked at your typical polyurethane that you would apply in the wastewater market as well. And for this study, it was an aromatic polyurethane. And then on the marine side of the business with ships, you know that they develop coatings that are what we call foul release coatings. And those are put on the undersides of the ships so that barnacles and whatnot, whenever they try to attach in the water, these coatings are developed to not allow that attachment to happen. So we decided to look at that in this study as well. And this specific developmental coating was using a binder that we term as PDMS, which stands for polydimethylsiloxane. And that type of binder is what they call super hydrophobic. Hydrophobic just means it doesn't like water. So if you have the super hydrophobic in front of there, then it really doesn't like water. So the next slide is going to show.
Yeah, so I'll just point out that we used that, we included that developmental foul release coating in this study just to see how the polysiloxanes would stand up against a coating whose only purpose was designed to release fouling in the marine industry. It's not a protective coating at all. So yeah.
So these photos here really tell a story. If you look at the photos, they go from looking at the very first big photo and moving clockwise. And this was looking at surface energy specifically. And whenever you're measuring surface energy, and these would be the droplets of the actual coatings on the surface, we're looking at that static contact angle. And we want that static contact angle to be above 90 degrees. So when we're looking at these images, if you look at the first one, the big one, that would be the siloxane 800. And fortunate, in this case, we have a contact angle that's greater than 90 degrees, which would be 92.6. That's an indication that it has low surface energy. And then if you move around, the ones that did the best or had above 90 degrees would be the competitors, polysiloxane, and then also the foul release coating. If you look at the amine epoxy, it's the one that actually has the lowest angle And that's not, in my opinion, a big surprise. And then the polyurethane didn't quite hit the mark either. I don't know if Steve, you have anything you want to add?
Yeah. So, these are water droplets on the coating surface, and the coating surface is not weathered, right? So over time, your epoxy surface is probably going to get worse than what it is right there because it's going to weather. It's going to chalk from the UV radiation. So you can see that the epoxy surface and even the polyurethane have no chance whatsoever of being an effective foul release. That's why the algae is able to so tenaciously hold on to those coatings and it's so difficult to remove. So I think Heather mentioned anything over 90%, 90 degrees is considered an effective foul release coating, foul release surface.
So this summarizes all of the results found in this study. The big column, or the important column to look at here, is the one on the right-hand side titled Surface Energy. And I would like to focus on the 22 seconds data, which is the bottom half of the chart. That 22 seconds is just the dwell time that the droplets were allowed to sit on the coating. And if you look at this, it's showing you that how the surface energy actually relates to the static, the static angle degree. So, yep. So, it's not a huge surprise that the foul release coating is getting the best results. And then you're looking at the polysiloxanes coming next.
Right. And the curve that they look at here, I can't remember what it's called, but it's not linear, right? So in other words, 20 isn't twice as good as 40. What they find when the people that deal with foul release coatings, what they find is that a coating becomes an effective foul release coating when it falls, when it gets to the 20 to 30. I don't remember what the units are on that. The surface energy is between the 20 and 30. It becomes a really effective foul release coating. You don't get a ton of benefit going way lower than that. And if you're above that, it's way worse. So you can see that the polysiloxanes both fall well within that 20 to 30 range. That makes them, in the people that deal with this stuff, call that a really, really effective foul release coating. Very close to the single purpose foul release coating that's under development that was 22.62. So we were a little bit surprised to find that, but pleased nonetheless.
Yeah. And then when we look at surface roughness, if you remember earlier, I said that ideally you want it as smooth as possible to be able to not allow stuff to attach to it. So whenever you look at the different information here. So just real quick, if you're wondering what some of this is, the SA is your average roughness. The SZ is your mean roughness. The SP would be your mean profile peak height. The SV is your mean valley depth. The ST would be your peak to valley height. And then SDS is the density of the summits. But if you look across the board in all cases, the Sherloxane 800 has very good results in regards to, or the polysiloxanes in regard to having that smoothness that we need.
Right. And keep this roughness, smoothness in mind, because if you are interested in using the polysiloxanes for foul release in any of the structures, we have to write a specification to make sure it's put on as smoothly as possible. Typically, these are going to be concrete. If they're steel, it's a little easier. But if you've got a concrete surface, we're going to want to do a resurfacing to get it the concrete smooth. Use an epoxy undercoat again to get it as smooth as possible. One thing that's interesting when they did this study, if you look at, we got foul release brushed and foul release drawdown on this list. And you can see the roughness of the brushed on material. The average roughness is 4.36, and the average roughness of the drawdown is 1.07. So they made a significant improvement in the roughness of the coating by doing a drawdown versus brushing it on. So we would recommend spraying the polysiloxane on in the launders over epoxy, which is over a resurfaced concrete surface, to get it as smooth as physically possible, to be as effective for as long a period of time as they can. We got a couple of things here. This is a fairly new one, so we just the results of this are going to be ongoing. But we did a launder in a clarifier in Hilton Head, South Carolina. This is the spec that we used here. They did a CSP 3 to 5 on the concrete, which is fairly rough. So then we put Duraplate 6100, which is a plural applied epoxy at 50 mils to smooth it out, and then the Sherloxane 800 over it at 5 mils. But this can all be, there's a wide range of undercoats and surface preps that we can do to make it as effective as possible. They did resurfacer with the just microsilica mortar. That's kind of what it looked like after the fact there. That we don't have a long, this is going to be ongoing. This is a fairly recent one within the last year. It so far has reduced the amount of time required to clean the algae from the launders, but we'll be interested in seeing how this works out long term. And Heather?
Yep. So then the final case study that we're going to talk about is one that was actually initiated and performed in 2020. So we have 4 years of this in service. And it was a chlorine contact basin where we applied a Duraplate 6000 reinforced epoxy at a high build of 60 mils dry film thickness. And then we top coated it with Sherloxane 800, which would be the polysiloxane at 4 to 6 mils DFT. And then the third party folks that we worked with on this were RFI Consultants, LLC, and Wilson Engineers. So basically in this project, what we did is took a section, a 10 foot by 30 foot section in the chlorine contact basin, and applied this system to it with the Sherloxane 800 as the top coat. And then we went back in to see how much the algae was holding on to the actual coating system, and then how easy it was to clean it. So Steve, if you could go to the next slide. So this is showing you a section of those 10 foot by 30 foot areas that I was referring to. And if you look at where the black arrow is, it is showing you where they clean the surface simply by using water and lightly rubbing it with their finger. And you can also see when you look at these photos that the amount of algae that was attaching onto these sections was a great deal less than what you're seeing on either sides of it, indicating that the coating is actually working as we wanted it to, as a algae release type coating. Next slide. These are showing you more close-up photos of the actual sections. So in that first photo is where they're rubbing it, and then you can see in the other two photos how clean it actually got just by that simple movement of wiping. Next photo. And then this is just showing you, another section, additional photos of the same section. You can see how white they got it down on the bottom when they did a full section of cleaning. And again, if you look on either side of these sections, you can see how there's a good bit more of algae attached to the coating systems than what you're seeing in that 10 by 30 foot section.
Yeah, Heather, oh, go ahead. No, I'm sorry. Go ahead.
Oh, I was just going to add that we did follow up recently with the folks that did this work, and they said that it is still working good after 4 years.
Yeah,
go ahead,
I was just going to give Bob Murphy a shout out. I think I saw him on the webinar here for initiating this project. And Bob retired from Sherwin, what, about 5 years ago? So if you're on here, Bob, shout out to you.
So this is just this was some quotes we got in regards to the owners and the observations of the actual report. So they said overall, the condition of the coating system in all 4 test locations appeared satisfactory, with no coating abnormalities being readily visible. The brownish residue that still remained on the tested coating system surfaces could be easily removed using water and lightly rubbing the surface. And the appearance of the coating system underneath the brownish residue still displayed good color and gloss retention. And like I said, we did follow up with them recently just to make sure that this is still the observations they're seeing.
Yep. Excellent. That's really all we have prepared for this webinar here. It's a fairly simple subject. If this is something anyone's interested in, all you have to do is you can contact us, contact your local rep, contact your PDM, your BDR, whoever you're in regular contact with, and we can help you develop a plan, a specification to give it a try and see if it solves your algae problem. So, Heather, you got anything else?
Well, we did have one question that came in that I did respond to, but just for the group. The question was, are you planning on obtaining NSF approval for the coating? And my response to that is, we're always considering new things to add to our product line. And I could see us doing that, down the line or in the near future. But as of right now, we don't have anything.
Are there any it says here, another question here, are coating systems the same for metal or concrete substrates? So in general, yes. The concrete requires a lot more coating though to cover the profile and to get it smooth, but you're still going to be talking about an epoxy primer and the polysiloxane top coat, just probably far less thickness than is required on the concrete.
And then there is
the chat. Did you see the chat?
Yeah. So there's a question in the chat. Will seaside area enhance algae growth? Do we need extra coating in seaside area tank? So
I don't know the answer to that.
Yeah, I'm assuming you mean that if it was like a wastewater treatment by the shore, I mean, in those cases, I would say that, if you recall at the beginning of the presentation, I was talking about how you need sunlight and the time of sunlight, the duration of the sunlight and temperature can affect algae growth. So it depends, I would say, on what shoreline you're talking about. Like if it's in the Northeast, you're not going to have the temperature as high. So that's going to help slow it down, but you're going to still have a good bit of daylight. Whereas you move south, you get more daylight and more temperature. So I think the answer to that question is it just kind of depends.
All right. I had another question over here. Will this bond to FRP? I believe it will, yes. With proper surface preparation, there's no reason you couldn't use it on any substrate you would use an epoxy on. So yes, it would bond to FRP. Question, can we have a copy of the presentation? Yeah, Heather said that during the intro, you might have missed, but you will receive an email after within the next day or two. Heather, is that the case? Or Kendall, a day or two?
Yep. So
and it'll have a link to the presentation and the PDF version of the presentation, correct?
Yes. Yep. So you get one email with the PDH credit, and then you'll get another email that has, I believe that has the presentation and the link to watch this recorded version of the webinar.
I got a question here. Will this inhibit bond of zebra mussels? I don't know. We've not studied that. It's my understanding that the zebra mussels adhere to surfaces differently than the normal biological growth does. The coating has low surface energy, so my very educated guess is that it will inhibit the bonds. I'm not sure it will inhibit the bond enough to make a difference over other coating systems. So that would have to be a study that would have to be done further to validate that out. So I don't know. I wouldn't count on it. Those things I understand are pretty tenacious. Chemicals leaching out of the coating. have any studies been performed related to chemicals leaching out of the coating? We haven't sent it in for NSF certification. That would be the main study to determine leaching. Beyond that, I don't know that there's any significant difference between the polysiloxanes or epoxies that you would normally use with chemicals leaching out in any significant amount. As I said, we're not talking about this right now for potable water. This is strictly a wastewater in an atmospheric solution, not a potable water solution. Let's see, we've got another one. Oh, God bless all. Thank you. All right.
All right.
That's it.